So, good morning. In this section, we will see the different boundary conditions. First, we will see dielectric interface. Now here, this blue line shows the boundary of two dielectric medium, and the upper one is medium 1 and the lower one is medium 2. Okay. And the permittivity of medium 1 is epsilon 1 and that of medium 2 is epsilon 2. And as I said earlier, every vector component can be resolved into two components, that is normal component and tangential component. So here E is a vector field, that is electric field intensity. It has two components, that is the tangential component ET1 and the normal component EN1. Tangential component means a component which is parallel to the surface, and perpendicular or normal component is a component which is perpendicular to the surface. Similarly, here you can see E is resolved into two components, that is ET2 and EN2. Okay. Now, in order to find out the condition of ET1 and ET2, what I am doing is I am placing a small closed surface A, B, C, D, E across a boundary of this dielectric medium. Okay. And this AB is having a length of del W, BC is of height del H, CD is del W and DA is del H. And this is a closed surface, this is symmetric, and we are assuming that half portion of the BC lies on the first medium and remaining half in the second medium. Similarly, half portion of AD lies in the first medium and remaining in the second medium. Similarly, CD lies in the first medium and AB in the second medium. Now we will make use of Maxwell's second equation in the integral form to evaluate the boundary condition of E. So this is a Maxwell's second equation, E integral E dl is equal to 0. Here we have a symmetric closed surface A, B, C, D, so that I am rewriting the expression as integral A, B, C, D of E dl equal to 0. Now we have to find out the total electric field over this closed surface. Okay. Now coming to this closed surface, we can see here I have marked two components, that is ET1. This is the tangential component across your first medium, and ET2 the tangential component across the second medium. Okay. So now I am going to find the total electric field across AB. So AB is a tangential length. So the total electric field is ET2 into del W. Now I am going towards BC. BC actually it is a perpendicular line. So here it will be having a normal component. As I said earlier, half portion of BC lies on the first medium and half portion of the remaining half in the second medium. So here it has two normal components, that is EN1 and EN2. Okay. So the lower section of BC will be having EN2 and the upper section of BC will be having EN1. And since it is symmetric, the upper section of BC, which lies in the first medium, will be at a distance of del H by 2 from the boundary, and similarly the lower section of BC, which lies in the second medium, will be del H by 2 from the boundary. Now we can write the expression. This much of portion, till this portion the total electric field is EN2 into del H by 2, because it is lying in the second medium and it is having a perpendicular component, plus this much of portion EN1 into del H2. Okay. Then we are moving across CD. CD is a tangential line which is lying in the first medium. So it is having a tangential component E T1 and the length of CD is del W. So I can write the total electric field across the CD is ET1 into del W. Since AB and CD are in opposite direction, this will be having a negative sign. So I can write the total component is minus of ET1 into del W. Now similarly DA, the arrow is pointing in the downward direction and half section of DA is in the first medium and the remaining half section in the second medium. So here you will be having two normal components because the line DA is a perpendicular line. So it will be having only normal component. So I can write the upper section will be having a component E N1 into del H by 2 and the lower section which is lying in the second medium will be having En2 into del H by 2. Since across BC we took the sign as positive, across DA you have to take the sign as negative because both are in opposite direction. So finally I can write the expression as ET2 del W plus En2 del H by 2 plus En1 del H by 2 minus ET1 del W minus En1 del H by 2 minus En2 del H by 2 is equal to 0. Finally I will get ET2 del W minus ET1 del W equal to 0. So I can write ET2 is equal to ET1. So that I can say that the tangential component of electric field is continuous across a boundary. Now we have the relation flux density is equal to epsilon E. From that you can find E is equal to D by epsilon. So if you substitute this expression in this, we can write dt2 by epsilon 2 is equal to dt1 by epsilon 1. That means the tangential component of electric flux density is not continuous across the boundary. So that's all under this section. Next, the second section we will see what happens to dN1 and dN2, similarly En of this dielectric interface. Okay. So for that what we have to do is we have to use Gauss law. According to Gauss law, you know that the closed surface integral of D dot dA is equal to Q. This is our Gauss law. Now in order to find the boundary condition of dN1, what we have to do is we have to choose a cylindrical surface which is a Gaussian surface. So here I have chosen a cylindrical surface of height del H and this is my first medium, second medium, and epsilon 1 is the permittivity of first medium, epsilon 2 permittivity of second medium, and the electric field is here I am drawing a plus sign and minus sign. So the electric field will be moving from plus to minus. So the electric flux density will also be in the direction of electric field. So along the upper end surface of the cylinder, dN1 will be like this, and this is the lower end surface of the cylinder, and here also dN2 will be in this direction. So point to be noted is that the electric flux density will be in the direction of electric field. Now as we studied earlier, if you are choosing a small vector area along the surface of the cylinder, it will be always be perpendicular to the surface of the cylinder, and also it will be pointing outwards. So this is the direction of dA when we come across the upper surface, and similarly this is the lower surface, and if I am choosing a small area dA, it will be perpendicular to the surface and it will be pointing outwards. The point that you have to keep in mind is dA will always be perpendicular to the surface as well as it will be pointing outward. Okay, the surface dA will not point inwards. It will always be pointing outwards and will be perpendicular to the surface. So, and h is the height of the cylinder. Now what we are doing is, I am assuming that as del h tends to 0, we will be having only two end surface. As this tends to 0, what happens? We will be having only this and this. Okay. So I am rewriting the expression as integral d dot dA of upper end surface plus integral d dot dA lower end surface is equal to surface charge density into dA, because we know rho s is equal to charge per area. From that, q is equal to rho s into dA. Okay. Now I am expanding the dot product. D dot dA is equal to d dA cos theta. Similarly, the same thing here, d dA cos theta. In the upper end surface, d and dA both are in same direction, so the theta value will be equal to 0. In the lower end surface, dN2 and dA are perpendicular, but they are in opposite direction, so the angle theta will be 180 degree. Okay. And the total flux density of your first surface is dN1, and the total flux density across a second surface is dN2. It is given in the figure. Okay, dN2. So when I am substituting d as dN1, I can remove the integral, because dN1 and dN2 are the total electric flux of medium 1, and dN2 is that of medium 2. So here I can see I am substituting dN1 as d for the upper end surface and dN2 in place of d for the lower end surface, and I am removing the surface integral. So finally I can write dN1 dA minus dN2 dA is equal to rho s dA. Then all the dA can be removed. Finally I will get dN1 minus dN2 equal to rho s. This is the expression for electric flux density's normal component across the boundary. Okay. Now if you are assuming that across the boundary it is free of charge, then rho s will be equal to 0. If there is no charge, then rho s will be equal to 0. Then we can rewrite this expression as dN1 is equal to dN2. So we can say that the normal component of D is continuous at the boundary provided it is free of charges. And similarly we know what is d? D is equal to epsilon E. So if we are substituting that relation in this expression, we will get epsilon 1 E1n is equal to epsilon 2 E2n. That means normal component of E is not continuous at the boundary. So in short we can say that across the boundary of a dielectric medium, the tangential component of electric field and the normal component of electric flux density is continuous, while the normal component of electric field and the tangential component of electric flux density is not continuous. So that's all in this section. Hope it is clear, and thank you.